So for the extra credit, I'll be doing chapter 10 end of chapter questions. The first end of chapter question that was assigned is 48. Consider the following boiling point data: compound methanol, ethanol, propanol, butanol, and pentanol. Here on the side we give our boiling points. Okay, the question is boiling points of these compounds increase steadily from methanol to pentanol. Which type of intermolecular force is primarily responsible for the steady increase of boiling points from the methanol to pentanol? So first thing that I noticed is that the carbon chain gets longer as we go. So to demonstrate how what intermolecular forces is responsible, we're gonna start with drawing the Lewis structure for all of these. So starting with methanol, that'll be, let's see, CH3, H. This has a total of 14 valence electrons with carbon, 4 hydrogens, and then 1 oxygen. That's gonna be a total of 4 valence electrons. We put 2 of this, so we get a total 14. So I can see right here, this is polar. Looks like all of these are gonna be polar because of the OH tail. So all of these are gonna be polar. So IMFs for all of this, and it has OH. So all of these are gonna have hydrogen bonds. So they're all gonna have London dispersion forces, dipole, and hydrogen bonds. I'm still gonna draw all of the Lewis structures, though. So that'll be 1, 2, H, OH. This is going to have 20 valence electrons. Okay, because of the 2 carbons, 1, 2, 3, 4, 5, 6 hydrogens, and then 1 oxygen, will get total up to 20 valence electrons. IMFs are London dispersion forces, dipole, and hydrogen bonds, H bonds. I'm just gonna say H bonds. As I said, all of these are polar because of the OH. All of them are gonna have an OH tail. But as we can see, they are increasing in size. So I'm still gonna draw all of them. Next one, ethanol, propanol. So propanol is gonna be 1, 2, 3 C's. The OH. This is gonna be 1, 2, 3. That's 4 times 3 times 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1 plus a 6. We're going to get a total of 26 valence electrons. So then this is gonna total of 26 as I calculated. This is gonna be 3 times 4, 1, 2, 3. This, and then this is gonna be 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1, and then there's just 1 6. So that all adds up to 26 valence electrons. Same thing as I said. They're all polar. They're all gonna have London dispersion forces, a dipole, and H bonds. After propanol is butanol. 1, 2, 3, 4. So this has 4 carbons. And the OH. So butanol has, so it's gonna be 4 times 4 because of the carbons, and then this is gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times 1 for the hydrogens, and then plus a 1 6. That's gonna be 32 valence electrons for butanol. So we put the 2 lone pairs on that. This is polar. This is gonna have LDF, dipole, and hydrogen bonds. So last one, pentanol. This is going to be 1, 2, 3, 4, 5 C's. 1, 2, 3, 4, 5. drawing this. And then our OH. So this is 1, 2, 3, 4, 5. 5 times 4, and then this is going to be 12 times 1 for the hydrogens, and then plus the 6. So that's going to be 38 valence electrons. So that's why I put those two right there. IMF, London dispersion forces, dipole, and H bonds. Okay, now to get to the explanation, I wanted to draw all of these so we could see that the carbon chain grows as we go down. So that's why there's a steady increase in the boiling point. So I'm gonna write my explanation down. Let's see. Okay, so before I write it down, I'm gonna explain it. So let's see. London dispersion forces are primarily responsible for the steady increase in the boiling points from methanol to pentanol. So all of these compounds have the same intermolecular forces. As we can see, LDF, dipole, hydrogen bonds. They're all polar. Due to the polar OH group. So as I said, so that being H bonds and dipole forces, right? The steady increase in boiling points is due to the increasing length of the hydrocarbon chain. So surface area / like size of the compound gets bigger, and the molecular weight increases as you go down. So we could see that this gets bigger. So this is London dispersion forces. This is this is related to London dispersion forces. As a compound is bigger, or molecule is bigger, it's gonna have the stronger London dispersion forces. So as I said, stronger LDFs require this more energy to overcome. So this results in a higher boiling point. So that's why we see a steady increase. So although hydrogen bonds are the more dominant force, the increase in boiling points across this series is primarily caused by the increasing strength of the LDF. So writing that down, I'm going to write that down for us. Of explanation is London dispersion forces is primarily, or let me write it down and then I'll read it. Okay, so I wrote down literally everything that I just said right now. So this is my explanation. Okay, so this is question 111. Carbon tetrachloride has a vapor pressure of 213 torr at 40 Celsius and 836 torr at 80 Celsius. What is the normal boiling point of Cl tetrachloride? So what we're going to be using is this formula. Ln times P2 over P1 equals heat evaporation over rate times the changes in temperature, T1 minus 1 T2. So if we what we're looking for, let's see, what is the normal boiling point? So we're going to rearrange this to heat vap equals R times Ln times P2 over P1 over 1 over T1 minus 1 over T2. So that is what we're going to be looking for right now, just as of right now. So we're going to input everything that we have. So heat evaporation equals our rate. Our rate for this is we're going to be using 8.314 joules over moles times K. So we're going to be using times Ln, and then we're going to do pressure 836 torr divided by 213 torr. Okay, and for 40 Celsius and 80 Celsius, what we're going to do, we're going to add that with 273.15 and 80. 273.15 because we want that to get that into Kelvin. So if I input that in my calculator, let me see, 40 plus 273.15, we get 313.15 Kelvin. And then this one's going to be 353.15 Kelvin. So that's going to go on the bottom. So 1 over T1. T1 is, let's see, 40. So it's going to be 313.15 Kelvin minus 1 over 353.15 Kelvin. So first what we're going to do is we are going to divide 836 torr divided by 213 torr. So if I do that, 836 divided by 213, that is going to be 3.82. So we're going to do 8.314 joules over mole times K. We're going to multiply that by, okay, so multiplying that by 3.92488, we're going to, then I already inputted this into the calculator. So this is going to be, we're dividing this and this. So 0.003193 K minus 1 minus 0.002831 K minus 1. So then inputting that into the calculator, okay, so then I get 8.314 joules over mole times K times 1.367. So we multiplied ln this and this, and then divided by, and then I subtracted this to get 0.000362 K minus 1. Inputting that into the calculator, we get, okay, after putting it in the calculator, I got 31395 joules over moles. Okay, so the heat evaporation is going to be 31,395 joules over moles. We're not done yet. Next step we're going to do is ln P3 over P1, and then equals heat evaporation over 8, and then 1 over T3 minus 1 over T1. Okay, so let's see, ln over 760, that's going to be P3 because 1 ATM is equal to 760 torr. So that's why P3 is this. So 760 torr over 213 torr equals, and now we have our heat evaporation, 31395 joules over mole divided by the rate, 8.314 joules over mole times K, and then times 1 over temperature 3 minus 1 over 313.15 K, and we get this from up here. So we're looking for T3. So then inputting this into the calculator, I'm going to pause it. Okay, so inputting that into the calculator, I get ln 3.568, and then I inputted all of this, and then I get negative 3776 1 over T3 minus 1 over 313.15 K. Okay, so then going to divide this on both sides. Okay. So, first let me actually calculate this. Okay, 0.273, and dividing it by the negative 3776. Okay, so then this is going to be negative 0.00037, sorry, equals 1 over T3 minus 1 over 313.15 K. Okay, so what we're going to do is, I'm going to divide this first. So I'm going to do that. There we go. All right, that's going to be 0.00037 equals 1 over T3. And then now that I divided that, that's going to be 0.003193. We're going to add this on both sides. Okay, so then doing that, 0.002856 equals 1 over T3. So then T3 equals 1 over, and then bring this over here, 0.002856. And then, and then that is going to equal, putting that in my calculator, 1 divided by 0.002856. So I get T3 equals 350.14. Okay. And there we go. That's my answer. Okay, I forgot one more thing. So with 315.14 K, just to convert it back to Celsius, it's 350.14 K, and we're going to subtract that by 273.15. I'm just going to input that in my calculator. So 350.14 minus 273.15, and we get rounded up to 77 Celsius. So answer is 77 Celsius. Okay, so this is question 125. An ice cube contains enough water at 22 degrees Celsius to make 18 ice cubes that each has a mass of 30 grams. The tray is placed in a freezer that uses CF2Cl2 as a refrigerant. The heat of evaporation of CF2Cl2 is 158 joules over grams. What mass of CF2Cl2 must be vaporized in a refrigeration cycle to convert all of the water at 22 Celsius to ice at -5 Celsius? The heat capacities for H2O solid and H2O liquid are 2.0 joules over grams times Celsius and 4.18 joules over grams times Celsius, respectively. And the enthalpy of fusion for ice is 6.02 kilojoules over moles. So I already started here. We have 18 ice cubes, and each have a mass of 30 grams. So we're going to multiply that. And what we get is 30 times 18, we get 540 grams. That's the mass total. So to get Q1, we have to do M times C times change in temperature. So that would be 540 grams times the constant, and this is for, let's see, liquid. We're starting off with liquid, so that is 4.18 joules over grams times Celsius. And then we're going to multiply that by 22.0 minus 0. So if I get my calculator, so that will be 2,257.2 joules over Celsius. That's, we multiply these two, and then we're going to multiply that by 22.22 Celsius, and we get 49,658.4 joules. Okay, now the next thing is enthalpy of fusion for ice is 6.02 kilojoules over mole. So this is going to be for Q2. So I kind of got stumped. I didn't pay attention to my units at first, but so for this 6.02 kilojoules over mole, we want that to be joules over grams. So what we're going to do is we're going to do 6.02 kilojoules over moles, and we're going to divide that by the 18.02, the grams of H2O, grams over moles. Okay, so now we're going to get, let's see, we're going to get, this cancels out. We're going to have 0.334 kilojoules over grams, or that is 334 joules over grams. So that is for Q2. And that's not for Q2, I'm sorry. That's for the enthalpy of fusion for ice. So now for Q2, for actually solving for Q2. So that's going to be 540 grams times 334 joules over grams. Grams cancel out. And what we get is, what we get is 180360 joules. So that is for Q2. So next for Q3, we're going to do the same thing, M times T times change in temperature. So that's going to be 540 grams times, now we're doing for solid, H2O solid. H2O solid is 2.03 joules over grams times Celsius. So times 2.03 joules over grams times Celsius. And then change in temperature is going to be 0 minus -5 Celsius. So now let me calculate that. So we're going to get 10962.2 joules over Celsius. We're going to multiply that by 5 Celsius. And we're going to get 5,481 joules. So now next step, what we're going to do is going to get Q total. So we just add up all of our joules together. So 49,000.4 plus, where is it? Oh, here we go. Okay. Plus 5,481 joules equals, and I'm just going to input that in my calculator and add those all together. So we get 235,427.4 joules. Now, this is not what we're looking for. There's still one more step. So what is this asking for? Let's see, where is it? What mass of CF2Cl2 must be vaporized in the refrigerating cycle? Okay, so now that we have our joules, what we're going to do to get the mass of the refrigerant is we're going to do Q total divided by heat evaporation. So that's going to be 235,427.4 joules divided by, and then our heat evaporation is 158 joules over grams. So 158 joules over grams. And then we're going, joules cancel out. So then we're going to put this in the calculator. 427.4 divided by 158. So we get 1,490 grams. And that is our answer.